out. Okay, so we are starting the session. Let me share. Okay, and this is the one that we want to talk about. Great. Do you see the shared page?
Yeah.
Good. Okay, so previous time we talked about hardness of n to the 3 or n cube, and the fact that all pair shortest paths, the conjecture, the big open problem is that all pair shortest paths needs at least n to the 3 minus epsilon for any epsilon greater than 0. It means that we cannot get truly subcubic time for that. And we mentioned a set of problems. We talk about the radius, we talk about like this betweenness centrality, and we talk about diameter. And I mentioned that for diameter, also it's a big open problem whether it is equivalent of all pair shortest path or not. So here we are proving a few of these things. For the, if you want to see the rest, you can just go and read some of them from the other paper, like this is the one actually that has the lots of these results. Here we are talking about a few results. We talk also about approximation that for diameter and betweenness there is such a thing that m to the 2 minus epsilon implies a strong ETH is false. Now, given all of this, let's go to the and see some problem. This is the problem of negative triangle that I will come back and define it. This is a very central problem in this paper that we discussed. They get lots of this result from negative triangle. They say that first the all pair shortest path and negative triangle are the same, and then from there they are getting the other results. But before that, let's see a few things, example, and then we will go there. Good. So the first problem that we want to do it is this problem. That, let me actually make it a little bit larger. Good. So we say that if there is a T of n and m, n the number of vertices, m the number of edges of a graph for positive betweenness centrality. So positive betweenness was exactly this problem, that you are given a graph and the vertex B. You want to see whether there is any shortest path from S to T that goes through B. That is, in that case, the positive betweenness means that the betweenness of B would be greater than, so betweenness centrality would be of B is greater than 0. That's the question. That's a positive centrality problem. Good. Now, it says that if there is a TNN time algorithm for positive betweenness centrality, then there is O tilde n TNM time algorithm for diameter. So, and this is important. So, O tilde, we are using it a lot. Generally, when we use O tilde, means up to poly-like factors. Means that if there is a poly-like, we can just hit it. And that happens a lot, that we don't want to discuss about the poly-like. These are like a constant. Good. Now, so here we want to have it. First, we want to say that if we have a procedure for positive betweenness or a function for positive betweenness, then we can, that procedure can solve diameter as well. Let's see, I mean, this is actually one of the easiest ones. So we want to solve diameter. First, we are assuming that the diameter is, I mean, an integer, but we want to say that it is even. Why? That's easy, because these graphs that are given to us, all the weights that are given to us, we just, all the weight of any edge here, we just multiply it by 2. So that, of course, all the distances become even and diameter becomes even. Now, what do we do? This is the things that we are doing. We just add another vertex B, and we put the distance from B to every other vertex d over 2. So this is a whole graph. We are adding a vertex B, and the degree, the distance from this guy to this guy is d over 2. Now, this is the interesting thing. It is easy actually to see that. What is d? By the way, d, to find exactly, we can do binary search. So that's the technique that we can do it. Binary search essentially would be log of the weights. And here we are assuming the weights even are polynomial. So that would be, with the log iterations, we can actually find what is the diameter. What we can guess the diameter. Now, what will happen if the diameter is d? This d, we can try this one. D is the largest integer that betweenness of BC of B is greater than 0. So D is the largest number such that betweenness of B is greater than 0. Now, why is it? Because if the diameter is less than d over 2, so consider the diameter, the pair that have the some distance less than, like equal to d. For these guys, always, yeah, so consider, say, these 2, 0, and 1, these are the diameter pair. Because if there is a diameter, there should be 2 pairs, of course, that they are far from each other. So if the distance between this guy, so if the distance is greater than, so if the distance between these two guys is greater than diameter d, then what will happen? For them, it would be beneficial, instead of going through the graph, they are using through B. And in that case, of course, the betweenness of B becomes greater than 0. So if the distance is greater than D, they should go through B, and that means that betweenness of B should be greater than 0. So D is the largest value such that the BC of B is greater than 0. Because as soon as D is greater than the diameter, like half of the diameter, then it is not beneficial that to go into D, and it would be better to go to the distance, to the distance in the shortest path in the graph. And here by betweenness, actually, I mean, we are considering fractional. I mean, what are the fractional of the shortest path that goes through B? And here, if there is a pair that, if there is a path that goes through B, it means that, I mean, essentially we are still less than diameter, less than or equal diameter. Is this clear to everyone? Please unmute and answer. Any question? But if there is something not clear, please ask me. It is important. Good. Now let's see the other one. That actually is the reverse that we want to talk about. So we talk and we mentioned that somehow diameter is harder than positive betweenness. Okay. Now, what about the reverse? Can we say positive betweenness also is harder than diameter? Okay. This is the next lemma that we have. We say that a given TNM, M is the largest weight that we have, time algorithm for diameter. Then there is O tilde NMM, time algorithm for positive betweenness centrality. So in some sense, diameter also can solve the positive betweenness. So what is the reduction actually that we are doing now? Good. So here, this is the one that we are doing. Consider this graph G. This is the graph that is given to us that we want to solve essentially positive betweenness. Consider any vertex V. For any vertex V, we are adding two extra vertices, VA, and the other one is VC. By the way, in the positive betweenness, we are given also a vertex B here. So we want to see whether so the question here is whether BC of B is greater than 0 or not. For each vertex V, we are adding this one. And what is the distance that we are doing it? This is the one that we compute. So that would be the distance of, so here, what is the weight here? Yeah, so good. Here for this guy, so this is, you can consider that this is a directed graph. So the original graph is direct. So the distance from VA to V, so this distance would be D prime minus the distance of V to B. So this is the distance V to B. What about this distance? This is the one that we are putting. That is distance of D prime. D prime is like essentially a constant that we define later. This happens a lot that, I mean, like when we try to mention a theorem, we are giving some parameters and then we have some constraints on the parameter and later we will set them. So this one, we are putting the distance of D prime minus distance of B to V. So, and how can we compute the distance from V to B? So how can we compute the distance of B to V here? Please unmute and answer. Okay, so actually, the distance, this distance that we are computing, we are talking about here. So these are all. Yeah. So this distance, we can just do a. We can just do a all pair. We can do it a single source shortest path. We can essentially we run a Dijkstra algorithm first. Run Dijkstra algorithm, and if you remember, the running time of that was m plus n log n. So first we are just paying this m plus n log n, which is of course this is a subcubic reduction because this is essentially order n to the 2. So n to the 2 means that it is subcubic, which is because it is less than n to the 3. So we can from B we can compute all distances of the vertices from B, all distances to B and all distances from B. So that is easy because also. I mean, Dijkstra generally compute the distances of these vertices from B, but you can also reverse the set of edges, and you will compute the reverse of it, the distance of all vertices, the distance from all vertices to B. So both of these we can compute it with Dijkstra, and the running time is order n to the 2. Is this clear? Please unmute and answer.
Yes.
So first we computed these distances, all pair essentially from this, that is order n square, and we are fine there. Now, when we put these distances here, now the question is that, so we have added these new vertices. Now, what do? We just consider the diameter of this graph. What would be the diameter of this graph? So the diameter of this graph would be between these two vertices. So there would be two vertices from, so say this is the diameter of it. So we compute this one, we put these numbers there for these new vertices. We have 2n vertices that we have added. So everything is order n. And then we say that there is a diameter here. We compute the diameter pair. So say the diameter is between SA. Okay, so SA should be something like, so this is so this is the diameter, say, between SA here. And then it is here. So this is A. This is C. And this is TC. And these are direct. So the diameter would be some pair. So these are the diameter pairs. So I will say SA and TC, this is the diameter pair. Good. So this is the diameter pair that we have it. Now we want to, based on what is the diameter of this graph, we want to say whether the betweenness of B was greater than 0 or not. Okay, so let me just put here a little bit of more space here. Good. Now let's go back to this one. Okay, so what would be the distance between SA and TC? Let's write it down. So the distance between these two guys. This one. This. Make sure that is the case. Now let's go back to here. Okay, so actually these are gone. We need to just define this again. So let me just draw this part. Good. So here, I think that's the graph that we had it. Maybe I should just change this one to this color. Good. So this is the one that we had it, and then color. So here we had this vertex A, and this is here. This is the vertex C that we had, and this is the distance between this guy. So this was SA, and this guy was TC. And this was the vertex B that we had. And we wanted to see the positive betweenness. So betweenness centrality of B was greater than 0 or not. Okay, now let's just see. So this is the diameter pair after this Dijkstra algorithm. See, what is the distance between these guys? So the distance between these guys would be exactly this one. So the distance between, so it would be distance between, and this is as I mentioned. So the distance between SA and TC is equal to, so 2 times D prime, because each of them has a D prime, minus the distance of S to B, minus distance of B to T. Good. So this is by definition. This part was essentially, so let me, I can just actually write it maybe this way, that would be better. Let me clear this one. Yes. Okay, so this is D prime. So why? Because the distance from this guy, from here, this was this part. So D prime distance of S to B would be this part. And this other part was this part. Good. Okay, so one other term also we are missing here. What is this other term? Plus distance of S to T. Good. Now, in this case, you can say that this diameter would be less than or equal to 2D prime. Because we already had a 1D prime here and 1D prime here. So the only thing that would be less than 2D prime if this minus part is greater than the positive part. What is that? Exactly that is the meaning that B, so it means that the distance of S to B plus distance of B to T, that should be greater than, or that should be, yes. So yeah, that should be less than or equal to distance of S to T. So we know that this is always less than 2D prime because yeah. So if this distance, if the distance of SB plus this one, if this is larger than this distance, then this would be a larger value that we are deducting from 2D prime. In that case, that would be just in this case. So this negative part would be larger than the positive part, and the diameter would be less than 2D prime. However, if the equality holds, if the distance between these guys, so this is exactly the betweenness, this is exactly the positive betweenness of B that we are talking about. So if the distance that goes through B is equal to the distance of this S and T in the original graph, then we know that essentially positive betweenness of B is greater than 0. So when we create this graph, then we want to see whether positive betweenness of this graph B is greater than 0. We are just, computing the diameter. If the diameter is less than or equal, if the diameter is equal to 2D prime, it means that the positive betweenness of B is greater than 0. And now, what is the D prime? D prime, you can just only put a big number here. For example, the D prime can be 2 times diameter of G. And again, we can first compute the diameter of G because we can do that. And then we will put D prime a big number. Such that, why do we put it big number? To just make sure that, all the distances are positive. And by the way, what is the diameter of the new graph? The diameter of new graph would be at most 2 diameter here, 2 diam, because these 2 diam. So 2 diam here, 2 diam here, and 1 diam here. So also the diameter of this new graph would be at most 5 times diameter. So everything is scaled by only a constant. And if this, when we have this one, we know that the distance is, the diameter would be always less than or equal to 2D and happens to be exactly equal to 2D if the positive betweenness of B is greater than 0. Good. Is this clear so far? Any questions? Great. So let me clear all the drawings here. So let's go and define this negative triangle. So the negative triangle is the one that we want to use it for the next reduction. Great. So let's define this one. So what is a negative triangle? A negative triangle is this one. You are given a graph, undirected graph G. Let me. So here. So you are given an undirected graph G. With integer edges minus m to m. So for example, so here the distances that are given to us, it can be negative. The other one that we mentioned from 0 to m. But and here, like if you remember the previous time, we had the D prime large such that all edge weights are positive. But here we have negative weights. So this is the question: is there a negative in the graph? Is there a negative triangle in the graph? What is a negative triangle? It is a triangle that sum of these weights. So if the weights is V8, this is V1, V2, and V3, then sum of these V1s are equal to 1, 2, 3. this should be less than 0. So this is a negative triangle problem. These are, again, the graph is given to you, the weights are this, and you want to see whether there's a negative triangle in the graph or not. Is this clear, the definition? Please unmute and answer. Is the definition clear?
Yes.
Great. So let me clear drawings. Good. Now let's go and prove this one. So, by the way, so what did we prove so far? So, for example, we have proved this part, that this is the one that we proved, that the diameter and positive betweenness, they are equivalent. We showed both ways. Now, what do we want to show? We want to show this part, that the radius actually is harder than all pair shortest path. So if you know the radius of the graph, then actually, I mean, this is as hard as all pair shortest. Here we are using one theorem here. I mean, in this paper, they are showing that all pair shortest path and negative triangle, these two are equivalent. So this is the one that they are in the paper. You can actually see it. So that's nice. It's not that hard, but also you can just take a look at it. So now, and we know that, of course, all pair shortest path, if you have it, then radius is easy, because we discussed that you will go through all vertices and compute the distance, and you will find what is the vertex. You will find the center of the graph, and the radius there is clear. So the only thing that is remaining is this part. So we know that these two pairs are essentially, so all pair shortest radius is easier than all pair shortest path. We know that all pair shortest path and negative triangle are equivalent. Now, the only thing that is remaining, we want to say that radius. So we want to say that radius is harder than negative triangle. So we want to show that one problem, that is all pair shortest path and negative triangle, they are equivalent. We want to say that this radius is actually as hard as negative triangle. In this case, then we have proved the thing that we want to say, that radius is actually as hard as all pair shortest path. Because in some sense, radius seems a special case, as I mentioned. Diameter, we don't know. Still, the problem remains open whether we can improve it or not. But yeah, for diameter, still we don't know. But for others, still the problem, like whether radius is harder than negative triangle, that's the thing that we want to prove it now. Good. So let's so what do we want to prove? We want to say that we want to give a subcubic. This is the goal. We want to give a we want to show that give a subcubic reduction from negative triangle to radius. What's the meaning of that? It means that we want to say that radius actually can solve negative triangle. So what is given to us? An instance of a negative triangle is given to us, and we want to use the radius to see whether this graph has a negative triangle or not. And this negative triangle, the weights all are from minus m to m for some large m. Generally, we can even consider this m is polynomial, because we are considering the hardness. The hardness of these problems, you can consider the case that even m is polynomial in M. Now, so this is the graph G, it is given to us. And from graph G, we want to create graph H. So this is for negative triangle. And then from this, we want to create another H. This is for radius. And this is the important one. Radius, actually, we can solve it in. So from negative triangle, actually, we can solve it to from negative triangle, actually, we can solve the radius problem. Sorry, in this new graph, this is the graph H. In this one, we can solve radius. We want to say that in the original graph, we can also solve negative triangle. So let's. So how do we create this graph H? So that's the thing that we want to do it now. Let me just make this one smaller. So is the goal clear? Please unmute and answer.
Yeah.
Good. Yeah. So let's start with this graph G. So how do we create this graph H actually? So this is the graph G that is given to us. So this is the graph G. And this is the graph H that we want to create. So this is the graph H. What do we have for H? So in this graph H that we are creating, we have, as you will see, we have like 4 layers. So maybe actually I can just do it here. And makes this one a bit bigger. I think that might be better because then I don't need to create all of this. Good. So how do we create this graph H? So this is the graph G for negative triangle. And as I mentioned, this is the graph H that we try to create. So what do we do? First, we are adding a vertex B to here. Then we have this VI, VJ, VK, and VL. So these are the, so this is the vertex B that we are putting it, and then these are the copies that we are putting here. So these are the copies that here we have VI, this is VJ, this is VK, and finally VL. Good. These are all copies of, so all of them are equal to V of G. So these are 4 copies of G that we are, vertices of V that we are putting. Now, we have mentioned about the vertices, we should talk about the edges. So what do we do for each edge Wx in the original graph? So if we have an edge Vx in the graph, here we are putting the edge from Vi to Xj. Good. So each of these vertices have a copy in each of these, 3 sets that we have, Vi, Vj, Vk, and Vl. So now, if there is something between V and X in the original graph, then we are putting it here also again. We are putting between Vj and Vk. And Xk. And so on and so forth. So this is the, let me just do it with a different color. We have this edge here. We are putting exactly as copies is here. What are the weights? The weights that we will put it would be 2q. This q again, the parameter that we will decide later, plus what is the weight? This is the weight of Vx. What is, so this one is the weight of this is Vx. So this is the W of Vx. So the weight here would be 2Q plus W of Vx. Again, what is Q? Q will be a parameter that we decide at the end. So we are mentioning all things in terms of Q, and then we say that what is how large you can get Q. Actually, I mean, you can, here we can also mention it. So we will put Q equal to 3 times M. What was M was the largest, absolute value here. So everything between minus M and M. So 3 times M would be the value that we are putting. So far we are putting the edges between these guys. But there are some more edges that we want to add. So especially one other edges that we want to add it from B to these guys. What is the edge? So from B to VI, we are adding. What are the edges? The edges here have the weight 2Q plus M. So 2Q plus M is the weight of these guys from B to this vertex. Finally, last but not least, for any vertex here and any vertex here, so for any vertex V here and any vertex X here, we are putting an edge here of weight 2Q. This is if and only if V is not equal to X. So as long as V is not equal to X, the weight from this guy to this guy would be 2Q. By the way, just one thing here, I wanted to just. So this guy, if the edge between these two guys is W of Vx, the weight that we are putting it actually is Q plus, it's not 2Q. So here, in some sense, we have so 1Q here. So we have 1Q here, 1Q here, and 1Q. Plus the weight of these guys that we are putting. Okay, now this is the main question. This is the claim. The radius of this new graph H that we have created. So these are the 3 types of edges. Something between VI, VJ, from B to this guys, and finally from the VI to VL. These are some special edges that we are adding. But there we are adding the edges if V is not equal to X. This is the claim. The radius of the new graph H is less than 2M if and only if G contains the negative triangle. So we just compute the radius of this new graph H. And if the radius is less than 9M, then we know that there's a negative triangle. Otherwise, there is no negative triangle. So is the claim clear?
Yes, it's clear.
Good. Okay. Now, so this graph, this is H. This is the same graph H that we have it here. So these 2 graphs are the same. So I may work in both of them. This is in this one or in this. Now, also note that, what about the edges? So the number of edges that we have here, I don't know, we have maybe 3 times the number of edges or 4 times the number of edges that we have it. The number of vertices, the number of edges, and the weights that we are having, all of them are within a constant factor of the original graph. So everything has been just changed by a constant factor, which is fine. Because, if we change the parameter, for example, if we go from n to n square, then this is not a good reduction, because then the running time of if you want to compute in the radius of n square set of vertices is different from the radius of the n graph, n vertex graph. So, but here we don't change anything. Everything is within constant factor of each other. Now, let's prove this one step by step. The first claim is this one, that if R, we want to say that a radius, we will compute the radius of this new graph. If radius is less than m, then this center should be, the center should be in I from this guys. So we want to say who is the center. So center was the one that essentially that maximizes the radius. So we want to say that center actually should be in I. Why is it the case? We can just consider the other options. So if you consider any, so this vertex B, so this vertex B, and a vertex here. So the distance between this guy, so this guy is 2q plus m. And what about the distance between this guy? So from B to all these guys, so consider, for example, Vj. The distance between them is actually would be 2q plus m plus the q of w of vx. So we want to say that actually the vertex B cannot be the diameter, because in that case, actually you can, if we are assuming these other things, that m is larger than, m is the, say, consider the weight of the graph, the weight of the vertices, and say, what is the absolute value of the, so this m is equal to actually max of a weight of E plus 1. So M is a little bit greater than just 1 plus the maximum. This is the absolute value because these are negatives. So consider the, what is M? The parameter M is the maximum absolute value of the weights plus 1. And what is Q? Q is equal to 3M. Good. Now what do we have here? So if you consider the vertex B, the vertex here, the weights would be 2Q plus M plus Q plus W of weight of Vx. But we know that weight of Vx is less than M. So we know that the essentially distance from B to any other vertex here, Vj or Vk as well, so because there are some edges here, that would be greater than 3q. Why? Because here we are putting essentially 2qm here, and then q plus w here. And we know that the weight is less than m because of this definition of m that I have mentioned. So we know that from B to this guy, the distance would be greater than 3q. And what is 3q? 3q is equal to 9m, the one that we were discussing. So if the distance is less than 9m, so we know that B cannot be the center. Similarly, we can actually say that J or K also cannot be the so the center cannot be also in, so the center cannot be in, so this one cannot be in B, the center. Because of the same reason, also it cannot be here because the B is far from here. And also it cannot be here and here as well. So in some sense, the center cannot be in any other place except I. Good. Because the distance of those guys from B is already greater than, or at least they are 3q. Which is equal to 9. And we know that the radius is less than 9m. So the center can only be in VI. So let me just clean it a little bit here. Good. So we know that the center can be only in I. Now, let's consider this VI. So we want to say when will happen that the distance from, so we know that there is a possible center here. So this is a center here, which is considered this. Now, let's consider what are the weights here. So the weights from, so in that case, the distance from all vertices to from this vertex to B would be just 2q plus m, because B is connected with such a weight. Good, so that is fine. What about this other guy? So the weights from, okay, so what about the weights from this guy to, this is, I mean, essentially connected if there is an edge between, so what is the weight between these guys would be q plus w of vx. So from this center to every vertex here, we know that the weight, the distance would be q plus w, and this w is at most m. So it would be q plus m, and q was 3m, so it would be at most 4m. So at most 4m from C, we can go to Vj. Here, to go from here, you need to pay another q plus wx, which would be, so q would be again 3m plus m here. So that would be 4m. So from C with 4m, we can go to J. And then from here to here, we can pay another 4m and go to J. So far, everything is good. Because, I mean, the distance from C to this B is fine, is less than actually 9m. From to J is less than 9m, and to K is less than 9m, which is at most 8m. Now, what about C and this guy, C and L? C and L, the distance, we put special edges from C to all vertices here, which was at most 2q. What is 2q would be 6m. So it means that actually from C to all vertices in L, almost all vertices we are in fine, except the C itself. Why? Because we have this kind of edges that I'm saying, from any vertex here to any vertex in L, except the C itself. So we are fine everything except for C. Now let's compute what is the distance from this to this. Let me just erase a little
Professor,
bit. Yes.
I have a question.
Yeah.
So what if there is like no edge in the original graph between some vertex and like we
yes,
like if you are connecting with like VI,
all the so if you are assuming that all weights are there essentially, every weight is between minus m and m. This is the definition.
So there is an edge. There is an edge between every pair.
Yes.
Of vertices.
Yes.
Okay.
M is the largest one. So if there is no edge, we can put m essentially very large. As long as it's polynomial, it should be fine. But yeah, we have a complete graph in that sense. Good. Now let me just erase a little bit here. So good.
Also another question.
Yeah.
So I think you cannot directly go from the vertex C in VI to the vertex C in VJ, because there is...
No, you can't go there. That's by definition.
From the vertex C to the same vertex in VJ, because there is no edge, right? Between C and C.
No. Sorry. In that case, yeah, I mean, we can actually put here. Yeah, that is good. So you can actually put just that is fine. From C to C here, you can just put the exactly Q. So if the vertex, you can assume that there is a self loop. from vertex C to itself in the original graph. And the weight is 0. So it is fine to here to go. Let me just do this one. Yes. So here, I mean, he actually said that. What about the C here? From C to here to C here, which would be the weight would be actually exactly Q. Because we are assuming that what is the weight of C to C would be 0.
Okay. In that case, we can also go from C in VI to C in VL.
How much would be 3Q, correct?
No, there is also another edge of like weight 2Q from above. Right? That's how you constructed it.
Yes. No,
so,
no. So you see, from here to here, from here to here, and from to here to here, that we have it. But this guy, the direct guy, there is no such edge from C to C here.
Oh, okay. Okay, sure.
So there is no direct guy from C to C here.
Okay.
That's exactly the catch. So yes, there is this Q, there is another Q and another Q, but there is no such so there is no such. So there is no such vertex, such edge of 2Q from C to C. Of course, I mean, one way to go there, you can maybe use another 2Q. So maybe you can go from here. So this is also one possibility. You can go by with Q here, with 2Q here, and then come back here, and then come back here. But then you pay another Q here and another Q here, and that would be just too much. Plus, I mean, some weight of these guys, but the weight of these guys, the maximum negative that you can get it is 2m. So it would be 2Q, it would be 4Q minus 2m. But 4Q minus 2m would be essentially 10m. Because, I mean, these are undirected graphs. So here you can go here. In the triangle, actually the triangle, these are undirected cases. So you can go here and then come back here and then come back here. But still you get it 10m. So, and now coming back to this example so far. The only problematic case that we have it is between C and C here. That, as I mentioned, if you want to go direct, so now if you want to go directly, see what would be the thing. So good. No, here, as I mentioned, so here you are paying Q plus the weight of these guys. So Q plus W of essentially C and, I don't know, here, for example, C and X. Then here, again, from here to here, you can pay another Q. So this is another one, which is Q plus W of, I don't know, X and, for example, X and V. So you go here. And then from here to here, you can also pay Q plus W of V to C. So we can go there. What would be the distance between these guys? Would be 3Q plus the weight of 3X. So what is this weight? This is exactly this one. So this is C, X, and V. And this is the W of CX. This is the W of XV. And finally, this is W of CV. So how much we are paying here? We are paying 3Q because of these Qs. So we are paying 3Q. We are paying 3Q here, 1Q here, 1Q here, and 1Q here. Good. So we already paid 3Q here, plus this weight of this triangle. The weight of this triangle that we have it here. Now, if there is a negative triangle, these three parts that we have it here, this part plus this part plus this part would be negative. It would be less than 0. It means that in this case, the radius, the distance from C to itself would be less than 3Q, which is equal to 9m. And we are done. So the only way that you can go from C to C here with less than 9m is that there is a triangle in the graph such that the sum of these weights are less than 0. Because if the sum of these weights are less than 0, then it would be 3Q plus some negative number, which would be less than 3Q. And 3Q is equal to 9m, and we are done. Is this clear?
Yes.
So we prove that this radius of this graph is less than 9m or 3Q if and only if there is a negative triangle in the original graph. And that's exactly the thing that we wanted. So we want, essentially, we say that the radius can actually solve the negative triangle. So that's a nice one. That's probably the most complicated one that exists in the paper. I mean, you can see that paper for other things. These are interesting things. As I mentioned, the diameter and all pair shortest path still is a very big open problem whether these are equivalent or not. So that's, I think, probably it is only at Zoom that I can use so many colors in a page, which actually is needed such that I can explain the whole idea. And now the good thing is that everything is recorded. So it is not just this slide, or this is not a lecture note that you need to read it. Now you can actually see the whole proof somehow video captured. Okay, so let me clear all the ranks, and we are done. So good. So here, actually, we are done with this part. This concept of subcubic equivalence between all pair shortest path and this other problem. So we were mainly, so here we discussed this particular case now that we show that these are actually equivalent. In this part, you can read it from the paper. Good. And now next time, actually, we are going to another problem. So from subcubic and subcubic, from cubic and subcubic reduction, we go to quadratic, n square, and subquadratic reduction. In particular, we talk about a problem which is threesome. And so what is the problem for threesome is that there are a set is given to us, a set A is given to us, and with n numbers. And you want to say whether there are 3 numbers A plus B plus C, which is equal to 0. Let me just change this one. So we want to see that there are 3 numbers, and A and B and C, they can repeat of each other. So it can be the case that A is equal to B. So it can be the case. And this problem actually is not, we will talk about it. It's not hard to see that this problem actually, you can get a n square algorithm for that. And this is actually one of the problems that they are asking in some of these interviews. How can you get n square here for these problems? Or some variations of that. Because, for example, in the threesome, instead of threesome, we can also define foursome. So foursome is exactly the same problem that you want to find instead of 3 numbers, we want to find 4 numbers such that the sum is equal to 0. And here, as I mentioned, you can have a repetition. A can be equal to B even, or B can be equal to C, or all of them can be equal to each other, but in that case, all of them should be 0. So then you need to only check whether 0 exists or not. So these are the 3 sum, 4 sum, 5 sum. Actually, these are a set of things that gives us some kind of hierarchies for this problem. So for this one, there is a simple, I mean, there is a simple like n square. I mean, n square log n is much easier, but you can also make it n square. And the question is that, again, the assumption is that you cannot do anything better than n square for this problem. Now, given that, what other problems are hard to solve? That's the one that we are talking next time about this 3 sum and its other variants, which are all of them. So these are the question here is n square hardness. So we believe that there is n square, but nothing better than n square. At least, I mean, this is the current conjecture. And we are talking about this. So this is the quadratic. And we are talking about subquadratic reductions. Subquadratic means that n to the 2 minus epsilon for some constant epsilon greater than 0. Great. So that's the thing that we try to do it. And we talk more about it next time. So any questions? So if not, yeah, please just spend time on your projects, and also the scribe notes, please do it as soon as possible. I mean, solve the assignments, etc. But yeah, the main thing, please work on your project. That's very important. And we will have something that we can present the presentation in the class as well. Great. So having said that, I think talk to you next time. Bye for now.